We actually have two, well, we got a little bit out of chapter, section 1, but then we've got sections 2 and 3, and once you catch on to the process, I don't need to do every example in the book because they all work the same way. Okay? One thing that I need you to know, this is that these two videos are recordings basically of just section 3.1. This one is from my class that I recorded last night. This is all of chapter 3 from beginning to end. I will warn you that video sound quality is not excellent because the acoustics somehow in that classroom makes it sound like I'm teaching in a barrel. But it is there, and I'm still recording this class for you. So if you miss class or you miss something in your notes, you'll be able to make it up. So let's get started. And we are going to need the calculator a little bit. So I'm going to get mine turned on and cleared off. So this is where we left off last time, I think. Because I kept these in order and set this aside. So this is going to be on page 5 of your notes. So a little quick review. We've got a system of equations here, or a system of inequalities that we need to solve. And the only way to solve a system of inequalities is with a graph. No other way. Graph is it. These two in particular simply tell us that x is 0 or larger and y is 0 or larger. And that just tells you you're going to be in the first quadrant. And for the most part, in all of our applications problems in this chapter, you're going to be in the first quadrant because you can't make negative anything, you can't sell negative anything, you can't buy negative anything. So we're mostly going to be in the first quadrant. So then we have these other two equations, and just a quick review of the process. If you have 2x minus 5y is equal to or less than 10, what you want to do, the first step to solving these is to graph the boundary, which is the equation that corresponds to this. 2x minus 5y equals 10. And because that's equals to, as long as your sign is either equal to or less than, or equal to or greater than, then your line that you graph, whether it has a positive or a negative slope, is going to be a solid line. Now, if we have any where we actually only have less than or greater than, when we graph the line, it's going to be a dashed line. And it'll either have a positive or a negative slope, or sometimes the lines may be vertical or horizontal. But that's the way that you tell. If it's equal to, you go ahead and make the line solid. If it's not equal to, it's just less than or greater than, you make your line broken.
Is it I always, when I'm doing my inequalities, like I put negative 5y is less than or greater to negative 2x plus 10.
You can do it that way, but you don't have to, because sometimes when you do them like that, what happens is when you multiply or divide on both sides by a negative number, you have to remember to flip that sign around.
Yeah.
But if you do it the way I'm going to show you to do it, you don't have to remember anything about flipping signs. We're not going to do this algebraically. We're going to do this to where you can actually just plot 2 points and get your line. So the two favorite points to plot are your x-intercept and your y-intercept. And you can get both of those by plugging in a 0 for the corresponding value. So if you want the x-intercept, that's going to be where y equals 0. And if y is equal to 0, that means that negative 5y is just going to disappear, And you can just kind of cover it up with your pencil or whatever, and what's left gives you your equation for x. 2x equals 10. That means x equals 5. So that gives us the point 50. We do the same thing with the y-intercept. We're going to let x be 0. That means if you cover up the 2x, you have negative 5y equals 10. And that means that if x is 0, y is negative 2. Because 10 divided by negative 5 is negative 2. So then you don't have to remember anything about inequalities or flipping signs around. You go and you plot these 2 points. So 0, negative 2, and even though I'm in the first quadrant, I can still pretty much guess where negative 2 is. So I'm going to go down 1, 2, and then 5, 0. That would be right here. And the only reason I want those is to be able to draw the line. So I get my ruler, and I make a solid line. And that line is the boundary, 2x minus 5y is equal to 10. Then I go and I look at the other one, x plus 2y equals 8. And I do the same thing. I see that my x-intercept, if I'm going to cover up my y, my x-intercept is going to be 8, 0. And then my y-intercept, which is where x is equal to 0, means I'll cover up the x, and that means I have positive 2y equals 8. And that means y, if x is 0, y is going to be 8 over 2, which is 4. So that means I need to plot the point 0, 4 and 8, 0. And then draw the line. So this is the line x plus 2y equals 8. And I have this point here, which is 0, 4. And I have this point here, which is 8, 0. And then I've got this point, which is 0, or excuse me, this is 5, 0. So I've labeled every single point except the intersection point. Now I don't know at this point if I need the intersection or not, so I'm not going to try to find it just yet. What I want to know is which way should I shade? Which side of the line should I shade on? And our favorite point to try, as long as it's not on the line, is always the point 0, 0, because it's easy to do the math. So if I look at x plus 2y is equal to or less than 8, and I plug in 0, 0, two times 0 minus 5 times 0 is still 0, and I need to know, is that equal to or less than 10? And the answer is yes. 0 is, in fact, less than 10. That means when I get ready to shade, I'm going to shade toward 0, 0. So I'm going to shade above the blue line. And then when I check in the other inequality, I have x plus 2y is equal to or less than 8. That means 0 plus 2 times 0, which is 0, is equal to or less than 8. And that's also true. So that means to go from this line towards 0, 0, I'm going to shade below the line. So what I can tell at this point is that if I'm shading above the blue line and below the red line, this is what's called my feasible region. This is where the solutions to my system of inequalities is. Because I'm shading that way and that way. This area wouldn't be shaded at all because it's not included in either area. This one would only satisfy, if you shade all this would only satisfy x plus 2y is equal to or less than 8. If you shade everything up here, then that only all of it satisfies 2x minus 5y is equal to or less than 10, but only this part of it satisfies both. So that area that satisfies both is called the feasible region. So that's where the solution is to all of the inequalities. Now we're going to go ahead and get into some terminology ahead of doing some of the other stuff that we're going to do in the next chapter. So let me go ahead and try to get some terminology going here. This is the feasible region. This point, this point, this point, and that point are the corner points. They're called the corner points of the feasible region. And at this point, I know my corner points are 0, 4, 0, 0, 5, 0, and whatever that point is. And the only way that I can find out what that point is to solve the system of equations that's created with these two boundary values. So in order to solve that system, we're going to go back and do things the way we would have done them in Chapter 2. We're going to solve 2x minus 5y equals 10 and x plus 2y equals 8 using matrices. And that's going to give us our last corner point. So even though we're done with Chapter 2, that hasn't gone away. So get the calculator, turn it on, go to Matrix, over to Edit, and our system is a 2 by 3. And its values are 2, negative 5, 10, 1, 2, 8. So we'll quit and we'll print out matrix A to be sure that it looks like it's supposed to, and it does. So then we go back again to matrix, over to math, to RREF, and ask it to find us the RREF, the reduced row echelon form of matrix A. And it says the solution to that system is 6.66666 and 0.6666. If we change that into fractions, all we have to do is hit the math button and hit enter, and it'll make that matrices that into fractions. So x is 20/3. And y is 2/3. So that makes that our final corner point. So that now we have all the corner points. So you do still need to remember how to do Chapter 2. Okay? Now what we'll do differently as we do the next few problems is we'll also have something called an objective function, and that's where these corner points are going to be very important. So be able to find your corner points. This particular example, the solution is a closed or bounded feasible region. Because it has a boundary around all four sides of it. Okay? If we look back at examples 3 and 4, which we did last week, find my 3 and 4. Okay, here's example 4. This is an open or an unbounded feasible region. And the reason it's unbounded or open is because it's closed in here, here, and here, but at the bottom down here, that continues on forever. So that one, it doesn't have a bottom on the feasible region. That feasible region goes on to negative infinity. And the same thing, let me find example 3. Okay, here's example 3. Example 3's feasible region is in here. And that's also an example of an unbounded or open feasible region. Because it's closed in on this side, it's closed in on this side, but it's not closed in out here. That's what it means to be bounded or unbounded. So one more time, we're going to find the feasible region and reinforce the idea, but then we're going to go on and do some applications in the next section. So we're going to graph the feasible region for this system. Notice that it says y is equal to or less than 1. That means that I'm going to have to figure out where 1 is going to be. And I'm going to only include everything below a horizontal line through it, y equals 1. So I need first to find my boundaries. So again, I'm going to go for the boundaries. This one would be 3x plus 4y is 12, negative 3x. And if I let y be 0, that means my x-intercept is going to be 12 divided by negative 3. So 12 divided by negative 3 is negative 4. And then I'm going to find my y-intercept, which tells me I'm going to let x be 0. So if x is 0, I have 4y equals 12, and that means y is equal to 3. So I know that I have to plot negative 4, 0 and 0, 3. Then for my other equation, 3x plus y equals 6, my x-intercept, I choose y to be 0, which means 3x is equal to 6, and that means x is equal to 2. Then I choose X to be 0 and find my Y-intercept.
It's supposed to be X plus 3Y.
Oh, thank you. Is that you, Sierra? There's your bonus point for catching me. So let me redo this because that number's not going to be right. X plus 3y equals 6. So if y is 0, x is 6, not 2. And then if x is 0, y is 2. So I know that I've got to have the point. This one's going to be, the y-intercept here is going to be 0, 1. So it's just going to be a horizontal line. This point's going to be to the left of the x-axis, or to the left of the y-axis. This is going to be to the right, and both of these are going to be to the right. So probably a good way to draw my axis, thinking ahead a little bit here, I'll choose my x-axis to be right here. And I'm going to choose my y-axis to be up here. So that I have plenty of room to plot points that I know that I have to plot. I'm going to let each one of these little squares be 1. So the point -4, 0, -1, -2, -3, -4, and 0, 3. 1, 2, 3. So there's my first boundary line. And then I need to plot 6, 0. 1, 2, 3, 4, 5, 6. 0, and 0, 2. So there's 0, 2. And then I'll draw that line, and it's also solid because it says equal to or greater than. And then I also have one more line, and that's the line y equals 1. So I'm going to think through how I want to shade this. So I'm going to test 0, 0 and all of these inequalities. And looking at the green line, y equals 1, 0, 0 is below that line. So from the green line down. I'm not going to go above the green line. Then 0, 0 in -3x plus 4y gives me -3 times 0 plus 4 times 0 is 0. And is 0 equal to or greater than 12? No. So since 0 is not equal to or greater than 12, and that's the blue line, I need to shade above the blue line. And And then the last one I'm going to check is 0, 0. 0 plus 3 times 0 is 0. Is 0 equal to or greater than 6? And again, the answer is no. So that means I'm going to not shade towards 0, 0. From the red line, I'm going to shade up in this direction. So here's what I've got, and I'm actually going to use the shading this time because it's going to make it a little more obvious that there's not an answer to this one. I'm going to go below the green line. But I'm going to go above the blue line. I'm sorry, I'm going to go above the red line and the blue line. Is there any place on that graph where you see all three colors overlapping? This one's blue and orange. That one's just orange. That's just blue. This is just pink. And even if I carry the pink on out here, where I've got some pink and blue, it's not pink and blue and orange. And if I bring it on out here, I have pink and orange, but not pink and blue and orange. And since the three regions don't overlap,
What does that mean? There's no solution?
there's no solution. That's right. There's no feasible region. And no solution. So if this was the set of inequalities that was for a business, and they were trying to determine what kind of solutions were feasible for their system of equations, they would see that they don't have any way to manufacture whatever it is they're trying to make because no values are in all three regions. Nothing can satisfy all the constraints. So that means they've got a product that they would like to manufacture, but they can't because they either don't have enough money, they don't have enough materials, they're not making enough money off the sale of it. There's some reason that they can't actually manufacture that product. It isn't feasible. The product is either too expensive to make or it requires parts they can't get. So there's always going to be situations in real life where there's really not an answer to what you'd like to have one to. So that actually kind of finishes up 3.1. Let's just move on. And we're ready to go look now at section 3.2. We need to get some vocabulary again. There's a lot of mathematical models designed to solve problems in business, biology, and economics that involve finding something called an optimum value. Now, an optimum value is either going to be a maximum or a minimum. If you're talking about things like profit or revenue, then I would think it makes sense that I would want to find the maximum amount of profit I could make, or the maximum amount of revenue that I could take in, because I'm making money. That's money for me. But if I'm talking about cost, I want to find the minimum value for the cost of whatever it is that I'm making so that I will have more of this. So I'm going to want to minimize that as much as I can without losing quality of my product. Okay? So in a linear programming problem, and that's what we're working on here, we have to find a maximum or a minimum value of a function, and the name of that function is the objective function. And that objective function has to satisfy a set of restrictions, and those restrictions are called constraints. Things that hold us back from doing just whatever we want to. Now, as long as we only have two variables involved in the solution, we can always find the solution by graphing. We may use matrices to find out where two lines intersect, but we will still be able to solve the solution, solve everything by graphing and finding the corner points of the feasible region, either by finding the intersections of lines or finding x and y intercepts. A corner point is a point in the feasible region where the boundary lines of two constraints cross. And that's where you're going to need your matrices. The coordinates of the corner point are going to be solutions to the system of those two linear equations. Okay? Talking here about equations, even though we're graphing systems of inequality. So let's see if we can work all the way through one example, and then I'm going to go on to the to an applications example rather than do a bunch that don't have anything to do with anything real. So here's our situation. First of all, we have this particular constraint. These are two constraints. And those two constraints simply tell us that our graph is going to be in quadrant 1. So there's our first two constraints. And we can just immediately solve our problem as far as those constraints by simply setting the axes up to be only for the first quadrant. So we've pretty much taken care of that constraint and that constraint by just starting the graph out the way that I did. Now I need to move to finding boundary values. So I take another constraint. The first constraint is 2x plus y is equal to or less than 4. I find its boundary by replacing the inequality with an equal. Then I find the x and y intercepts. So if x is 0, y is 4. If y is 0, x is 2. So I need to plot the point 0, 4. And I need to plot the point 2, 0. And then I'll draw the line. And it will be a solid line because it says equals to or less than. Now I'm going to do my testing of my points all at one time. So I'm done with that constraint at this point. So let's go to this constraint. I have negative x plus 2y is equal to or less than, which I'm going to swap out for equals, 4. That means if I let x be 0, 2y is equal to 4, and that means y is equal to 2. And then if I let y be 0, then negative x is equal to 4, which means positive x is equal to negative 4. So I'm going to go 0, 2. Then I have to go negative 4, 0. Now I still need that point, even though realistically it's not going to be in my solution area, but I need it to be able to graph this thing. So I've left myself a little room here, and I'm going to go backwards. 1, 2, 3, 4. So here's my point, negative 4, 0. So it's not even going to be in the solutions region, but it's going to help me determine what the solutions region is. So now the time has come that I need to actually test out my favorite number, which of course is 0, 0. So if I go to this inequality, 2 times 0 plus 0 is 0. Is 0 equal to or less than 4? Is it? Yes. So that means I'm going to shade towards 0, 0. And even though it's kind of hard to imagine that this is below the line, this is below the line. So I'm going to shade this direction. Then I'm going to test 0, 0 in the second constraint. Negative 0 plus 2 times 0 is 0. And again, we already know 0 is equal to or less than 4. So that means that for the purple line, I'm also going to shade below the line. So I now know what my feasible region is. My feasible region is this area right here. Because that's where everything's going to overlap. And so what I need are the corner points. So I'm going to scoop this up a little bit. And one of my corner points is 0, 2. One of them is 0, 0, but I'm going to tell you up front, 0, 0 is never going to be the answer. Even if it does give you the minimum value for the objective function, it's not going to be the answer, because if you don't buy any, you don't sell any, you don't make any, nobody wants to do that, because that means you're never going to make any money. You might minimize your cost to nothing, but if you don't make anything, you can't sell anything, so there's no point in being in business. So even though 0, 0 technically is a corner point, we're not going to use it as a corner point because it doesn't give us realistic answers. So our other corner point would be 2, 0. And then we need what is this corner point. And in order to find this corner point, we're going to take this set of inequality constraints, and we need to find out where our two boundary values intersect. So to find out where the two boundary values intersect, what we need is the reduced row echelon form of this matrix. 2, 1, 4, -1, 2, 4. And that will give us our last corner point. So we have 2, 1, 4, -1, 2, 4. So our third corner point is 4/5, 12/5. Now what we do with those corner points is we're going to take each one separately and we're going to plug in the objective function up here. So the objective function is z equals 3x plus 4y. And we want to find its maximum possible value. So what we're going to do is we're going to plug these values into this expression, do the arithmetic, and see which one of these 3 points gives us the highest value of z. That's what we're trying to do. So z for this first one would be 3 times 0 plus 4 times 2, and 0 plus 8 is equal to 8. Then we're going to plug in z equals 3 times 2 plus 4 times 0. 3 times 2 is 6 plus 0 is equal to 6. So we know already that's not going to be our maximum, because it's already less than the 8 we got on the first one. So now we need to plug in this one. Z equals 3 times 4/5 plus 4 times 12/5. And because the calculator works with us, we don't have any problem with being able to answer that. We say 3 parentheses 4 divided by 5, close the parentheses, plus 4 parentheses 12 over 5, close parentheses. And let's just get the answer as a fraction, then we'll get it as a decimal if we need to later on.
12.
Yeah, it's just 12.
Yeah, it just actually turns out to be 12. But we get a fraction just in case the answer does come out as an ugly decimal, and we would really like to have an exact answer. So this comes out to be 12. And since 12 is more than 8, then we now know that our maximum is reached at that corner point. So this is the corner point that will maximize our objective function. Let's see where I can put this so I can write that down.
How you gotta write the objective,
Yes.
maximum?
The objective function is maximized 12, which is the maximum value of the objective function, using the point 4/5, 12/5. Okay? So this is the whole process that we're going to follow, but we're going to do it in an application scenario. So I may skip a couple of examples here. I actually worked those examples in that other video. But in the interest of us actually getting finished up today and being able to have time to practice next time, what I'm going to do instead of doing this example, I want to go to an applications problem so that we can see how we actually are going to apply this, because it makes it much more realistic, since you're business majors, to actually put this in context of something that has some kind of meaning. So what we're going to talk about here is canoe rentals. Thomas Pinedo wants to start a new business called River Explorers. And he's going to rent canoes and kayaks. And the fact that he wants 10 people to travel, you know, wherever for how many miles, that's not the important part. He wants to rent canoes and kayaks. That's the takeaway from that first problem. Now, you can probably imagine, without going any further, what he's going to want to know is how many canoes and how many kayaks. That's going to be the goal. So what he wants to know is how many canoes and how many kayaks is he going to need to have to make the most money. Now, if he didn't have any constraints, he'd just go out and buy a bunch of canoes and kayaks and have no idea. But he has constraints. He has monetary constraints and he has spatial constraints. First of all, he has a total of $45,000 to purchase the boats. That means that his money cannot exceed $45,000. So down here on cost, we have to stay equal to or less than $45,000. It also points out to you that the canoes sell for $600 each. Well, he has to pay $600 for them. That's the selling price. So he has to buy them for $600 each. And the kayaks, he has to pay $750 each. So when you add $600 for every canoe and $750 for every kayak, he has to stay below that constraint of $45,000. That's not if I would like to. That's, you know, you're out of money, Jack. You can't spend anymore. You're done. So then the next part we look at is he also has a space constraint. His facility, where he's going to store all of his boats, can hold up to 65 boats. He can't buy more than a total of 65 boats. So the number of canoes plus the number of kayaks has to stay equal to or less than 65. Now at that point, we're really not going to need to know the next part of the information yet, but I'm going to make a note of what it is. Because this is going to be how many canoes and kayaks should he buy to earn the most revenue. Well, we need something about his revenue. Well, his canoes are going to rent for $25 a day, and his kayaks are going to rent for $30 a day. So this is how we come up with the objective function. and it's revenue. And of course, since it's revenue, we don't want to find the minimum revenue because we want to make all the money we can. So we're going to want to maximize it. So our revenue function, and we still use Z, although you could call it R if you wanted to. Our revenue function is 25 a day for canoes and 30 a day for kayaks. So that's what we want to maximize. So we're now ready to talk about constraints. So we've written that down. We don't do anything else with this until the end. What we need to do now is we need to find the constraints. And your constraints are x plus y has to be equal to or less than 65. And 600x plus 750y equals 45,000. And because we're talking about x is canoes and y is kayaks, that means x and y both have to be positive. So that means we're going to have to restrict our graph to the first quadrant.
Well, we know we're gonna have already had a couple problems with it. Well, we know it's gonna be in the first quadrant, we still wanna leave us some space.
I leave this down here just so that I can draw the points and
And
label
they'll
what they
have
are.
results.
Yeah, I always leave myself a little bit of space. So if I have to go to the negative side or
Yeah.
below, then I can. Okay, now, I've taken care of this constraint and this constraint because everything's going to be here. And this is where y is positive and x is positive. What I've got are these other two constraints. This one's not hard to figure out. If we have x plus y equals 65, then what we know is that if x is 0, y is 65, and if y is 0, then x is 65. So we can plot that one pretty easily. Then I'll look at this, and plotting 65, 0, and 0, 65 on an axis where I have these in hundreds, that's going to be really frustrating. So there's a little trick here that's worth knowing that you can do. If we take this objective, this constraint, 600, 750, and 45,000 can all be divided by 150. So what I want to do is I want to take this boundary and I want to divide every single thing in that whole equation by 150, because if I modify it that way, I haven't changed any of the solutions to it. If I divide both sides, I haven't changed anything. But I'll have numbers to deal with when I graph it that will be smaller. So I'm going to put all of these over 150. You don't absolutely have to do this, it just makes it easier to graph. And that means that this is equivalent to 4x plus 5y equals see, 15 goes into 45 3 times, so that would be 300. Now, I can manage those numbers a lot better than I can numbers that are in the 10,000s. So then for that constraint, if x is 0, then y is going to be 300 divided by 5, which is 60. And if y is 0, then 300 divided by 4 is 75. So I can find those points a lot more easily if I scale that down. So I'm just scaling it down. Still have the same solutions, but it'll be easier to graph now. So I need the point 0, 60, 10, 20, 30, 40, 50, 60. That's not very high. I wonder if I can go by 2s. So 10, 20, 30, 40, 50, 60. So 0, 60 is right here. And then 75, 0. 10, 20, 30, 40, 50, 60. That's not quite going to work.
15s will work.
15s will work. So I'm scaling here by 10s, but here I'm going to work by 15s. So this is 15, 30, 45, 60, 75, 90. So here's 75, 0. And I'm going to draw my line. And I'm going to check the point 0, 0 in the original. So 600 times 0 plus 750 times 0 means 0 is going to be equal to or less than 45,000. And that's true. So I know that I'm going to be shading toward the origin. So then I'll look at my other points, 0, 65, okay, 0, 10, 20, 30, 40, 50, 65, and 65, 0. So here's 60, and this would be 67 and a half. So that's probably pretty close to 65. So I'll connect up those two. And at this point, I'm going to go back up here again and say if x is 0 and y is 0, 0 plus 0 is equal to or less than 65. So I'm again going to shade below the red. Which means when I actually do my shading, this is going to be my feasible region. I have to stay below the red and below the green. So there again, there's your yellow feasible region. And that means then that our corner points, we're going to have to continue on to another piece of paper here. Our corner points are going to be 0, 60. And this one, which is 65, 0. And of course, 0, 0, but we know that's never going to give us maximum anything. So then we go up here and say, okay, we need to know where those two boundaries intersect. Where do they intersect? So that means we're going to have to solve the matrix equation, or find the reduced row echelon form for 1, 1, 65. And you can use these numbers or you can use the ones we transform with, but I'm going to go back to the original numbers since I'm just finding a solution to the same equation. So 600, 750, 45,000. Forgot to do reduced row echelon form. So it says 25 and 40. My last corner point here is 25, 40. So now that I've got my feasible region and my corner points, I'm going to take my corner points and I'm going to use my objective function and see which one of those gives me the maximum. So z equals 25 times 0 plus 30 times 60 is 1,800. Does everybody agree? And if I use the second one, z equals 25 times 65 plus 30 times 0, that's 1,625. So clearly, this does not maximize our revenue. So then we check the last one. So 25 times 25 plus 30 times 40 is 1,825. So that's not it either. This gives us the maximum. So then to answer the question, back in context of your problem,
Why is it 30 times?
oh, I'm sorry, it's 40. So Thomas needs to buy 25 canoes and 40 kayaks for a maximum possible revenue of $1,825 per day. Now it's kind of important that you put in its maximum possible, because if he rents out all of his boats, then that's where he makes the most money. He may not rent them all out, but that's still the best way for him to be able to achieve his maximum revenue. Okay? So be sure to write out your answers to these in a sentence. Now, I have one more here that we're gonna work on. What I want you to do, we're not gonna do it here in class today. I want you to go to example 2. See if you can work out example 2 without help, and then go check, because it's actually recorded in the other video, so you can check your solution to make sure that you're getting it right. Okay? And then the only thing left after that is the Happy Ice Cream Cone Company, and we're going to do that one in class together. Okay? So we should be good to go at this point. That should be everything.
On that chapter between the two, that there was a 2.4 question mark.
I had forgotten to do this, I will.